Okay, good evening, people. Numbers seem to be down just a trifle. First, quickly, week 8 exercises. There's a lot less programming here, so much so that I added a programming question just to keep you working on the seaside. The first questions are, and I haven't geared this stuff up for anything but programming questions in a way, so you've got .txt files, which are just simple ASCII. I could have PDFs and all that kind of stuff, but most of the solutions are really simple. Graph fundamentals, graph representations, storage costs, which is a really nice exercise. Depth and breadth first, very simple. And visited array, just so that you understand what the visited array does and does not do. And a little palindrome, which I'm sure you've done in Python and in some other language or in some other language. And here I ask you to do it in pseudocode first and then do a quick complexity analysis of it. So get used to that style. I'll try to do that every week now. A small programming question. First nut out what you've got to do in a sort of a C-like language. Forget the semicolons. You don't need that. You don't even need types. It's about getting the actions right, the actions, the sequence of actions and the loops that you need. There's no right and wrong in terms of syntax, really. And just to do a simple complexity analysis based on that, and then to write the C program. The idea with palindrome here isn't so much, obviously the complexity is an interesting issue in itself, and you don't need to think too long and hard about that, I think, because it's quite simple. But if there's one question that you give yourself a time limit, that would be that question. You don't want to spend 3 hours doing it. You'll fail miserably, in a manner of speaking. Okay, you really want to say, can I do this in 20 minutes? That's the kind of time period, certainly not more than half an hour. It's only a few lines of code. Okay, they're the exercises for this week. As you will have seen, I've opened up the solutions to week 7 exercises. I should just quickly here we're talking about the linked list ADT, the graph ADT, the graph adjacency list, and the graph adjacency matrix ADTs. These are all pieces of code that were missing in the lecture slides. Now, I have many versions of these ADTs, the graph and the queue, the quack, and I have them in the context of lecture slides, I have them in the context of exercises, I have them in the context of assignments and from previous years, and I have various different interfaces and different things you can do to quacks and graphs, and it gets quite a mess. So I cleaned it up a little bit just a few days ago, but there were a few problems with that, as a few students have pointed out to me today, and so I've gone back to what I consider the authority, which are the lectures, and in particular the graph lecture, which is presumably that Monday lecture. Yep, that'll be that Monday lecture. And when you go to the ADT for graphs, I define here the graph.h, the header file, and there the very observant will have noticed that some of the names have changed very slightly. I've tried to be more consistent, only for, well, the main reason is there are a lot of ADTs and I'm trying to get a consistent naming and passing of parameters. So you see that edge in line 16, 17, 18, 19 and 20, it's edge, it's not E. So I'm not doing edge new E or insert E or remove E. One or two or more of them were E's before and some of them were edges. And I'm trying to adopt a consistent notation of when there's a numerical argument to give that first, and the ADT data structure is the last argument that you give. So I've reversed the arguments as well. So you see there that the in line 16 to 20 graph is the last argument. And that reverses the earlier version of those functions. So these are just new names, but if you've copied, cut and pasted the old versions and have got something working with the old version, you'll find that I've moved on, if you like. The lecture slides have moved on to this slightly new name where you reverse the arguments and fill in the word E, will make it edge. So you'll need to do a little bit of editing. I would recommend you cut and paste this ADT now, from now on, and use that and modify your code if necessary. The reason that this is necessary is, well, quite apart from this is what I'll be using for marking purposes, so I'll compare your code against this. But also, for example, in the weekly exercises from last week, where you have to fill in particular functions like is edge and remove edge and functions like that, they, of course, interact with these others. So they should all have the same naming. So it's no longer just an E, it's a full word edge, just to get consistency in the interface. So that does mean, for example, with the AM, if you go to insert edge, is edge, not is E, is edge. There's only tiny changes, but if you've got, again, if you've got these ADTs, you should overwrite it with the new version here. And in the AL version, you'll find it's exactly the same thing here. New edge, show edge, is edge, insert edge, all consistently named. I've got a feeling why I didn't have that before has to do with the textbook. I think he does it in the textbook in what I consider an inconsistent way. And I've decided, well, let that go now. These are becoming so, there's so much change going on, I might as well give my own consistent naming. This flows over into quacks, which I'm going to change eventually, but not anymore this course, of course. So that's the graph stuff. What we want to go on to now is, that's wrong, got to finish that. So slight changes to the ADTs, back to the lectures. What I was doing on Monday was graph search, and I want to finish that off ever so quickly. Think about what I'm doing. The first thing I want to very quickly revisit is, as a student came up to me last week and pointed out that I was again not consistent. When I first, boom, 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 going back, I handled DFS quack. Now, here we go back into what are we doing? I introduced this concept of depth first search, and I said when you go down the tree in the depth first way, it works in a certain way, but you can get to a dead end, and there can be another branch of the tree which you forget, and that's a sort of an orphan vertex. It could be a whole bunch of orphan vertices, and you've got to backtrack to get to them. Well, not the only way. A way of backtracking is to have a stack, and every time you traverse, process, visit a vertex, you put all its adjacencies, all the vertices that are adjacent, on a stack, and then you process them. So if there are any children, all the children would be processed on the stack, from the stack, and that is your sort of inventory of vertices that have to be done. That way you can't forget anybody. So if you keep on, and if you have all your children on the stack, and you do one, and then you put more children on, and you do another one, and you put more, you keep pushing them onto the stack, and you process them, but eventually, as you process or traverse, you run out of children. And as you run out of children, you just pop. You keep popping the childless leaves, the ones at the bottom of the structure, ones that you've done you've processed all the kids already, so when they actually meet each other, you've already done that now, so there are no more children to be done. So you just continually pop the stack, so the children that went up there very early on, you get back to. That's how backtracking works. You store everything on the stack, and it's a stack. That means you pop, and you push to the same place. And that means the children and the grandchildren, the great-grandchildren, etc., effectively get put on top of each other and stack up. And then you try to work them off, process them, and that's when you start the popping business. And again, you can only do that when they become childless, so that you don't keep on putting things on. Okay, that's the basic idea of this quack. It's a self-contained little function, this DFS quack, but it handles only connected graphs as it is. It cannot, the reason, well, okay, maybe I should open that up to you. Why? What is there that stops it handling a disconnected graph? What is the most important line there? Yeah.
Because it only checks its children. Whenever, at the point where it starts, it only checks its children, and if something is disconnected, it will not have any connection between them, so it will not...
Yeah, you're looking at me. Tell me on the code, where is it? Excellent. First rate. Perfect answer. Just that one name is edge. If there's no edge, there's no way it's going to find a child. It must have an edge. And what have we got with a disconnected graph? No edge between the two subgraphs. So it just can't find them. It just doesn't know that they're there. It doesn't have any overview. It's not a human. It doesn't know. It just knows what it knows and it sees edges, and it just processes the edges, and that there's a little subgraph over there, maybe just one little node all on its own, maybe a massive tree graph, it just can't see it. Okay, so what I've done as a result of the criticism last week, I said, okay, here's the quack now modified to do disconnected graphs. And you see basically line 8, which is all visited is 0. I have that outside loop, which is outside the is the stack empty. So it's a while, a double loop. The inside loop, if I could call that the inside of the 2, does the processing of a subgraph, and it's happy, finished, the graph's the loop, the quack is empty, but it's got to check to make sure there isn't another subgraph there. And it can do that very effectively. We've got all the material we need. We look at the visited array. Remember that visited array tells you which vertices you're visited in the order. So they were all -1. For every node in the graph, you've got a -1 in the visited array. Now, every one we visit, we put in the order number, the position or the time or the visitation number. 0, then 1, then 3, then 2, then 3. It can be all over the place depending on the connectivity. And eventually, we'll filled in, we hope, completely the subgraph or the graph or the array. If it's connected, it's all full. So in that case, and you see the condition that we look at, or the thing that we do, is we have in lines 25 to 31, 32, I go through all, I assume that I visited them all visits now 1, and then I go through every single vertex and check whether visited of that vertex is unvisited. If there is one, just one, that's unvisited, then my all-vis gets put back to 0. I push that vertex onto the stack and I start over again. I come out again and then all-vis is still 0, and then I pop that vertex. Okay, so I go back to the outer loop. So all-vis terminates only, there's only one way that becomes 1, and that is when that for loop in line 25 does not or all the vertices have got a visited array element. There are no more -1s. Okay, so line 25, 26 should show that no vertex has not been visited. If no vertex has not been visited, we're finished. Now, if there are 100 components and there are 10,000 vertices, it will keep looking for unvisited vertices. And every time it finds one, it says, okay, the stack was empty, I've got a new one, I'll push it onto the stack and I'll go back to that all-viz, if you like, loop and start again with my stack, as if it was a brand new search. Okay, so that's how in a sense it's irrelevant. It has nothing to do with In a sense, it has nothing to do with depth-first search or any kind of search. You could do this with any traversal of the graph, breadth first, depth first, or any inside-out search you like. It's just a programming nuisance that it needs to be done if you want to handle disconnected graphs. I'm always tempted to leave it out, thinking it's not that useful, but as I did it with now when you go to the depth, shall I show that now? Well, before I do that, I've now split up the tests into 3 tests. If we just look at go back to the top. If you look at the contents, you see that there's depth first 2.1, the DFS stack, which is just what we've been looking at. I then have the disconnected version, the connected and the disconnected version. Again, it's only that all visited parameter or integer or variable that monitors that, so it's an extra loop on the outside. It doesn't really change the depth first at all, in essence. So I have 3 test programs 3 test runs in 4, 5, and 6 here. Then in section 3, I do recursive depth first. There's no quack. This is pure recursion, programming recursion. Okay, so there's 2 approaches to solving this depth first problem. One is using our own data structure, quack, and the other one is using pure programming. Both are very important. So when I look at the performance now, or the testing of test 3, a disconnected graph, you see here test 3, a disconnected graph for the quack version. There's my input file, 010212. Then 343545. 2 triangles. 010212. 343545. 2 triangles, okay? Does the first triangle, says I'm finished, but it's not, because then it goes through and sees, and you see here in the middle, right in the middle here, graph is disconnected. That's the message it comes out with, that's debug. Tells me, if you like, that it's found that there's still more to be visited. And you can see, well, as you can see in the visited here, 2/3 of the way up, -1, -1, they're the nodes that haven't been touched yet, or that's not quite 100%, that's 1 back. But there are nodes that haven't been touched, and it thinks it's visited, so it's got to continue on. So by the time when you get to the bottom, 0, 1, 2, 3, 4, 5, they've all been touched, they've all been visited. Okay. That was one version of DFS. Then I do the recursive programming version where there's no quack, so you hear seeing 7 and 8. I just need 2 ADTs, the helper, what I call my helper ADT, IOMEM, and the graph, of course, to read in the graph. You have to have the graph ADT. And this is most boring in a sense. It's just called DFS here, depth first search. We start as the starting point. Now, this is a very important function here. This is the wrapper, what's called the wrapper. It's the thing that actually sets things up. And the thing that has to be set up is, in particular, visited. Programming or quack solution, we need visited. We have to know where we have been. We must record that, otherwise we're going to end up going through a cycle and going round and round forever. We must not revisit vertices. So here's our DFS wrapper, and you see in line 33 and 34, visited and order are being set up, initialized, and as long as all vis is, so we have the outer loop, of course it's handling, connected. You can look at that and say, all vis, it's connected. It's disconnected. It's handling disconnected graphs. Okay, it keeps on looking for more nodes that haven't been visited. The important line here, the only important line really, is DFS-R. DFS with recursion. And it takes the start and the size, and of course these two arguments, order and visited, which have been initialized there in the wrapper. And we go into this little recursion now, where it keeps calling itself, trying to traverse the whole graph. And it will only be able to do that, of course, if it's completely connected. If it's disconnected, when it's finished, or when it thinks it's finished, it's got to check whether they're all visited or not. Do I do that really? Yeah. All vis equals 1, checks in line 40 whether indeed they're all visited. If they're not all visited, if there's something that's unvisited, I then, all vis is 0, start v equals w, so that's the w, that's the vertex that was unvisited, and I come back DFSR again with start v, a new start v. That first start v in line 38 came from my line 35, which is the root vertex. So the very first time the wrapper is called, you give it the starting point. You have to give it some starting point. It just doesn't guess something. So when you say, I want to do a depth first search, starting where? And it gives you, usually you start with 0, but you can start with any node. But you've got to tell it where to start. Once you've given that initial starting point, it's then up to it how to continue on. And the problem, not problem, but the issue is, of course, if you have multiple connected graphs, multiple graphs, subgraphs, then once it's got the starting point on 1, which is what I call there the root vertex, it processes that, and then it needs a starting point for the next one, and it gets that in that little trick. The start v equals w, 44, and then to loop back to the top, 37, and to go in again, DFSR, line 38 with start v again, a new start v. So the root v was used the first time, and every time after that, it's going to be the next unvisited vertex in the disconnected graph. If it's completely connected, of course, that doesn't happen. It doesn't go back again. All visit is straight away is made 1 in line 39 and doesn't change. Okay, so that's the gory detail. Too much already about disconnected. It's just not really interesting from a search point of view. What is important here is the actual recursion, the depth first recursion, line 53 to 60. And you see that it's a bit ugly in the sense there are a lot of parameters in that function, the graph, the vertex, the size of the graph, and of course the order and visited. We need those, all those parameters. We have to update the visited because we're visiting a particular node. We'll come in with a particular node. We're going to visit him. Okay, and then we're going to, and we have to put the order, we increment the order to say, okay, we've got one more that's been visited, and this is the order number. And then we go through, look for the adjacencies, and do those children, do those adjacent vertices. So the stack frame from the call frame from the computer is being used, in a sense, as a quack. But it's a programming stack. It's not a quack stack. It's not a hand or a user or a client control stack. It's a real recursion. The problem is that it's an expensive way of doing it, as all recursion is, because every time you recurse, it means you add a lot more load onto the memory. When you do it on your own, you've got complete control, and it's, in effect, iteration. Of course, you're just adding things onto a data structure, an internal data structure that you create yourself. So, but these lines are important. Sort of imprint that on your head, in your mind, The DFSR as a visit, an order, and then for all of the vertices that are adjacent, so that is 56 and 57, all of the vertices that there are, you check where there's an edge and whether it's unvisited, and then you go there. Okay, so 54, you update the visited because you've got a node, you give that node a particular order number in visited, so the -1 is gone, it gets a particular number of the order that this has happened, so this is continually updated, so every new node gets its own order number, could be anywhere in the on the whole graph, of course, depending on the labelling, and you take a child, which is unvisited, and you go there and you do the same thing. In this sense, you're going deeper and deeper to the children, to the grandchildren, to the great-grandchildren, etc., and then you come out again. Coming out again is just continuing on with that forward. So the DFSR comes back from a child or great-grandchild, and as it comes back, it does the others at a particular level and goes deeper again, it comes out and goes deeper and goes up. So it's going up and down like a yo-yo, and eventually, when there are no more children, it just keeps coming back. That's how recursion works. Same idea as the quack, but it's done in programming. Now, I went through that in a second time, in a sense, because I now want to confuse you by introducing, say, what breadth first is. Now, breadth first, here, I'll just show you the version which uses the quack. But you must remember for later tonight the DFS version. So we're going to be doing both, and you're going to have to think about each time which one am I doing. In breadth first, we visit row by row, in effect, or level by level, or adjacency by adjacency. It's a fairer way of doing things. It's a more democratic way. It's when the parent says, okay, something has to happen with that child and with that child and that child, and I don't, if the children are older, at first say, well, okay, to handle that child, I first have to do that child's children. And if you're that old, then your children's children, so you're going straight away and before you even finished all the children of the children of the children, and then come up to that child, okay, now I'm going to do you, and you do this whole tree. This is what depth first is like. Here we say, okay, we're going to do all three children, so we're going to do you, then you, then you. And only when I finish you three, I'm going to do the grandchildren. So you do all the grandchildren, one after the other. And then you do all of the great-grandchildren. So it's level by level, it's distance from the root, distance from the initial vertex. That's what determines the processing order, that determines the traversal. So here we have that same example before with depth first when we got to a dead end, and without the quack or stack, we couldn't get back to 2. But when we put them all on the quack, then we could find that there was still a 2 on the quack, and we still had to process that backtracking. Okay, that was with depth first, and now we're breadth first. So what we do with breadth first is 0 has 2 children, 1 and 2. We do both of the children, and then we look for both of the children's children. So who's got 1 got children and has 2 got children, and we do them. And in this case, there's only 1 has got a child, and 1's child has also got a child. So it's a great-grandchild, I presume you'd say. Child, grandchild, great-grandchild. So in essence, the vertices are processed in order top to bottom, left to right, as you would tend to naturally label them at. Now, the thing that you don't necessarily see with the stack, you can sort of work out, with the stack version, with DFS, you can sort of work out why the stack works. Interestingly, because it is quite unnatural. A queue is a much more natural thing, but the thing with a stack is you're working on the same place. You pop, you push, you pop, you push, and you sort of can work on that one spot in your head. And you sort of have a sense of it, things stacking up and coming off and stacking up and up and up and up, and then eventually coming down, 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 down. It's sort of a natural way of thinking, in spite of the fact that it's an unnatural data structure, because most things in life are really queues. First thing is first out. That's fair, that's democracy. You sort of expect the person who gets in there first can actually have the most, if you like, or get the most benefit and be out the first. Very unfair to say that the last person in is the first out. Crazy stuff. So, with the DFS, we pushed all the adjacent vertices onto a stack, and we pop the top of the stack until it's empty. And we keep pushing children on, and we keep popping off the stack. As long as we continue to work on the stack and make sure it's empty before we're finished, we're going to do it okay. It's sort of guaranteed correctness, if you like. The issue is that you're popping and pushing and popping from the same place. Now, if you're going to, in BFS, you do exactly the same thing, but you push and you don't, instead of push. And you use a queue instead of using a stack. And then, when you think of, you're doing exactly the same thing, but you queue, ushed, not ushed. So when you pop and push in the depth first, you're pop and push, pop and push. So that means that the children always come underneath the bottom of the queue, and you process from the top. And in a sense, that becomes immediately highly, just natural. You think, okay, I'm 0, I've got children 1, 2, and 3. I put 1, 2, and 3 on the stack, on the queue. Now, I'm only popping from the top, and when the children of 1 and 2 and 3 have children of their own, but they go underneath. They're cushed. So they don't, if you like, contaminate. They don't affect the logic. You just keep on popping and you pop them off in the correct order, the first in, first out order. So you do 1, and then 1's children get pushed onto the stack, onto the queue. Then you do 2, your second child, and its children get pushed from underneath. Then you do your third child, 3 comes off, its children get pushed. So the children are getting put on in order to, well, put on, they're getting pushed on from underneath. So you have the right order, first in, first out, and the order of the children and their children's children and children's children's children all go on from underneath and get processed in the correct order from the top. That's it. That's BFS. It's identical operation, except the Q instead of the P in terms of pushing, putting things on the data structure. And there are in fact just 4 changes. Here's BFS quack. The changes are D goes to B, so not BFS, not DFS, it's BFS in line 1. We've got in line 4, instead of push, we've got cush, so second letter has changed. In line 14, we've got another big change, P to Q, push to cush. But in line 12, you've got the change where we reverse the order. Here, we put them in the, if you like, the order of the children, the numerical order. Now, this is a complete irrelevance. You could adjust it easily on both DFS and BFS, picked up the order, numerical order if you like, or any order you want to name. It doesn't make any difference because in some sense, completely random. The labels on the nodes, on the vertices, are what you create. So in a sense, the order in that for loop is irrelevant. It's just tradition in depth first. You put them in there from big to small. So when you pop them, you get small to big. Okay, that's what we sort of noticed last week, which you may have forgotten that detail. But in any case, with cush, because you're processing them, because it's a queue, you can put them in, am I saying that right? Yes, you cush 1, then you cush 2, and you cush 3, then you pop 1, pop 2, pop 3. You get the right order by cushing in the right order. So if we use the same graph that I had before, and this is what actually you see happening here, I compile it, BFSQ, with my ADT and graph and the quack, and it visits 0, start off with 0, in that thing up there, 0, whoops, stop, go back. So 0 has children 2, 5 and 7. So 0 has children 2, 5 and 7. They get cushed onto the quack. 2, 5 and 7 are cushed, they're children. We visit the top one, that's 2. Its children, 2 children are 0 and 6. All the children go on, but when they've already been visited, they get thrown off immediately when they get processed. So 0 and 6 goes on there. You have 5 and 7. 2's come off. It's being processed now. And 0 and 6 have come on as the children of 2. And then we now do process 5. We put its children on, process 5, vertex 5. Its children are 0, 4 and 3. So 0, 3 and 4. 0, 3 and 4 goes cushed. So you cush the kids, pop the parents. Okay, it's really the same thing, but it's working on two ends. And eventually you come up with visited. There's the visited. Okay, that's it. So that's BFS, and that's DFS. We saw DFS two ways, two flavours, and we've seen BFS just using the quack. It's clean and it's neat. Okay, now that finishes the actual underlying data structure, the traversals. This is where it starts to get interesting. And you could actually say this is the part of the course that you're really starting to get serious now. This is now we're going to apply, in this particular case, graphs, and we can see what we can do with graphs. And this is where real research issues, and I've programmed, for example, you see applications here, breadth first for shortest path algorithms, and depth first for applications, cycle detection, Eulerian cycles, finding a path, whether does a path exist in the graph at all, and reachability. Reachability is massive in the research world, and in general, lots of applications want to know when you have a graph representing a mass of relationships between entities, is it possible to go from entity 1 to another, some obscure entity a long way away? Is there a path between the two? Is there some kind of obscure relationship? Can you do that efficiently? And it's a very interesting problem, reachability problem. There's a lot of theoretical work on that as well. So let's just take the first one. There's only one on breadth first. Breadth first tends to be limited in its applicability to shortest path stuff in general. I find that's the most useful thing, the thing that's always mentioned. And that is because it has this wonderful property. It handles the children democratically, if you like. All the kids get handled before the grandkids get handled, before the great-grandkids get handled. That means when you do find a node that you're looking for in a traversal, you know you've got the shortest path to that node. When you use depth first, you go deep into the tree and you could come to a node from underneath, if you like, from some obscure direction, and it could actually be right next to it. The labelling is such that you take this really long detour to get to it, and it could be right next door. So you don't want to use depth first for shortest path algorithms. It is a total disaster. There's absolutely no guarantee. You could do the whole graph and get finally to the node you're looking for, and it's next door. You just couldn't see it because it was just one too far away. So let's have a look at breadth first and shortest path. We had BFS quack. I just went through BFS quack. That's the name. I had DFS quack, now I've got BFS quack. And that did the children and the grandchildren, etc. We can just change the name and modify it ever so slightly and change our traversal, which is just traversing the whole graph. We think, well, okay, we traverse the whole graph, great stuff, but what good is it, in a sense? We've done it all, and we can be proud that we've done it all, but what have we achieved? Well, we've actually not been looking for anything. We don't have a goal as such at all. It's aiming sort of mindless. If we know what we want, then we can, of course, stop the BFS quack when we find what we're looking for. Some node with a surname, with an age, with an occupation, some relationship to the situation we want in the real world, the place we want to drive to, something that we want. We need to find the node with this particular property. Then, of course, we have to introduce that property into our BFS quack. And when we do find a node with that property, we just come out. Okay, we abandon the ship, we stop what we're doing, and we come out and say, we found them. And that's the basis of the BFS shortest. It's just a rewrite of BFS quack. And not the most serious part of it, but because BFS quack just had a starting point and just did the lot, did them all, children, all the generations, forevermore, and assuming it's connected or disconnected, it just does the lot. But now, we're interested in getting to a goal, so we have to tell the goal too. We have to define the goal as, in this case, it's simply abstracted to just a number. We want a particular goal vertex. We don't know where it is, it's somewhere in the graph. We have no idea where, how far away it is, but we want to find it. How do we find it? Well, we call BFS quack with two parameters in a sense. Instead of just the vertex v, I now say where we're starting and where we're going to go to. Okay, so that's the start is just v, and the goal is now new. We need to do two extra things. You could change BFS quack so that when it gets to this goal, when it finds G, the goal, G-O-A-L, when it finds it, you can say, yes, found it. That's easy. But where are you? How did you get there? Now, that's another matter. How do you retrace your footsteps? It's a bit like going into the jungle and you find what you're looking for, a person that's lost, but you're lost too. You don't know how you got there. You've got no sense of behind you. You don't look. You're just looking, and you do the traverse. Ah, found you. Where am I? I have no idea. So you're both lost, in a sense. Need some way of finding your way back out again. And the way you do that is a kludgy thing, a bit like visited was kludgy. And there's a sort of a visited array, but it's called parent. So every time, it works exactly the same way. Instead of recording in visited a particular order number, the visitation number, if you like, whenever you visit the node, and then you get all the adjacencies, and you put it on the data structure, you change the visited array. You've also got a parent visited, which says not only, which you set to also to -1s, and you set to your parent. So if you're vertex 5 in parent is the number, the vertex of the parent of 5. So every vertex in visited has a corresponding parent number. Now that tells you who your parent is. And if you think about it, it sort of makes sense. If you're 5 and your parent is 7, then in parent, index 5 will have 7. And if you go to index 7 in parent, you'll find its parent. Could be 12. So you go to index 12 and you find out who its parent is. And it could be index 2. Go to index 2. Who's its parent? Number 5,000. 5,000 all the way over there. Who's its parent? 0. Ah, you're back to the start. So you take the parent of the parent of the parent of the parent of the parent. And you're back to the original starting node. Okay, so that's the basic idea. So we have to do two things. We have to say, have we reached the goal? Well, it's just a comparison. Every time you get a vertex, you visit it, set the visit. You say, well, is this the goal? Yes, found it, I'm out of here. Then you undo, if you like, or you just get out. You don't have to clean the stack or anything if you don't want to. Just leave it all as it is. You just know you found the goal. But the one thing you're going to need is this parent array, because it tells you how you got there. It's your track. It's the way back. It's not backtracking, it's the track back. It's interesting, backtracking and track back. Oh, I haven't thought about that before, but yeah. It is the track back. So you've got the parent, which is the track back, and the whole data structure is, of course, for backtracking. Interesting. Okay, now, so all we have to do now is, how do we implement all that? I've explained all that here. Oh, yes, just one thing. The array parent enables us to retrace or track back a path back up to the graph, up the graph when we find the node. When we do find our goal node, we have a stack that we're popping. We're in the midst of pushing to, and so the thing's on the stack, and we find the goal, then we literally stop the loop because we've found the goal. We don't care about anything anymore, so we leave visited unfinished, and we leave parent unfinished, and we leave the stack with its members on it because we don't care about the rest of the graph. We have found what we're looking for, the goal node. Okay, so all of that, well, it's not actually that much. Here we have our Same main, 13 to 32. It's the same boring thing every time. Look at it, refresh yourself. It's the same thing. You set up the graph, and instead of calling DFS quack or BFS quack, it's now calling shortest path. Okay, and it has two parameters, or two arguments, instead of the one in the middle. I'm ignoring the size and of G and G itself. Start and goal. Okay, that's what shortest does. Needs start, needs a goal, needs to know what it's looking for. Goal. So that's our boring main program. That's almost always the same. And here's shortest path. And you see the basic, it creates the quack, it puts the start on the quack, sets up the order and the visited start off with, and as long as the quack's not empty, we're only handling the connected case here, we process all the children, we push everything onto the quack. I'm saying which edge I'm doing, and I'm reporting visited W in line 50, visited W. This is the standard way of doing it. Okay, I'm now doing child W. It's visited, and this is the order position or the visitation number. Then the next line in 51 is parent of W is V, because V was the node where we just come from in that for loop above. The 4 vertex W, all the children, and the 44 is the thing we popped. We want the children of V. We found the child of V, W, we've visited W, but we do not forget who V is. Don't forget your parent. Okay? Remember your parent, and then you can go back, because when you remember your parent remembers its parent, so you can go back to all the parents and find your way back home. It's crucial. So there's our parent, being that one line is really all that changes parent. Crucial to getting out the forest again. And the next 52 and 53 is, have we found the goal? If we found the goal, found is one, and we're out of there. And in 43, you see, if it's not found, you keep on going, but if it's found, you get out. You stop. Whatever the state the visit is, or visited, parent and state of the stack are irrelevant, forget them all. You just want to get out with that goal node because you found him. Okay? And the issue is then, you've got to not lose your parent as much as it could be filled in completely, or half, or a quarter, or a third, or maybe you're lucky you hit him straight away. In any case, the parent will have all the history, your family history. It's your family tree, in a sense, in an array. So, in line 59, we say, if we've found it, so we've got our goal, so you can say, well, I found the shortest path from start to goal, and I print the path. Now, this is tricky. One thing having parent is another thing knowing what to do with parent. Because parent, unfortunately, is upside down. If you think about it, you are some child of a child of a child of a child of some original root node. Now, you somehow you want to say, what is the path from start to goal? But you're at goal. So you've got to go back to start and then come back to goal again. That's what you want to do. You don't want to get the path in the reverse direction. You could do that, but it's just not what you want. You want the path in the right direction, which is start to goal, of course. But that's not what you've got. You've got the goal node, and you've got a parent history. And the parent history tells you how to get up there, doesn't tell you how to get down. And can you use it to get down? That's a bit of a problem. Not even sure that's going to work. How would you do that? You think yourself, you've got parents, but how do you know who the children are? Maybe it won't work at all. So what can you do? Well, it's a funny problem because you can go one direction, but you want the other direction. So if you go back, but remember each time what you're going back to, in other words, the previous step, and then you got to remember each of these steps in some way, but when you get to the top, you want to be able to undo or see everything that you've sort of saved, all the steps. You want to save every step back. in fact, what you want to do is when you take a step back, if you make that recursive, then you take a step back, so you've got the goal function, if you like. You then get you call print of the parent, but before you print the parent, you take the print of the grandparent. But before you print the grandparent, you take do a print of the great-grandparent, and before you do that, you go back, 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 but each time it's recursion, back, 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 until you get to the root. And then when you get to the root, you print the root, but you're umpteen levels sort of down, but you're actually coming out the graph. When you're up the top, you can then unfold everything and say, okay, now I'm ready to print the child of the root, and now I'm ready to print the grandchild, and now I'm ready to print them all. So you first go back recursively. Before you print anything, and you only start printing when you get to the top. It's a beautiful example of head recursion. So that's what's going on in print array. So let's explore that a little bit more detail here. Print path. It's taking the parent and the goal, and it's going to print backwards. So I'm going to go backwards to go forwards, and I'm using head recursion. We'll explore that a little bit more in a moment. Here, when I'm finished all of this, or there's no path found at all, of course. If you give it a node number which is just not there, well, okay, just bad luck, it'll print no path, so there's nothing to print. So at the end here, just for debug, I have a look at visited and parent to see how much of the arrays were actually used in the process. And I do the right thing, and I free visited, free parent, and do a make empty. Get rid of all the rubbish, or all the stuff I left behind. Just realise as well that the first two lines in shortest path, which again is BFS quack, just changed slightly, line 35 and 36, they're just mallocs. Okay, I do a malloc, local malloc. Those are the array data structures that I use to store the visitation and the parentage. Okay, so I run it on that same graph again, and this is the output here. It comes up, here's the graph there, find shortest path, that's the request. Find shortest path, that comes from the main program. Doing edge 0, 2. Now what? So 0, 2, 0, 5, 0, 7. Remember, it's based on BFS and it does the children first. So 0, 2, 0, 5, 0, 7. They all go on. Then it says, okay, the first child is 2. Now I need the children, and I process 2. 5 and 7 underneath it. Okay, they were pushed on. Now it's doing the children, now it's doing 2. To do 2, it needs the children of 2, which are 0 and 6. So the children of 0 and 6, have I said that right? Or have I just completely? Yeah, 2, 5 and 7. 7, what's it doing? Now I've lost myself. Oh, I'm looking at the graph itself. 0, 2, 0, 5, 0, 7. Now it's the children's turn. 2, 0 is nothing. It says, okay, 0 has been visited, so it does 2, 6. And then it says, okay, now I'm finished 2. I've done the children of 2, which is 6. 6 has been pushed onto the crack. And then it says, okay, now 5 is next, and then 7 will be next. So who's the child of 5? A little bit more. Who's the child of 5? 3 and 4. So I put 3 and 4 on the crack, and 4 is the magic number. 4 is what we're looking for, the shortest path from 0 to 4. So the moment 4 gets on, we're finished. We've found the shortest path. And it's, in fact, I'm printing it out, 0, 5, 4. How did I print that out? Using print path. So print path is interesting, and here's visited now. We can see visited, and we can see what parent looks like. And parent gives, for those nodes there, 0, 1, 2, 3, 4, 5, 6, and 7, who the children are. Interestingly, 0 and 1, it didn't get to. They stayed unvisited. Now 0, sorry, not visited, they stayed unparented. 1, it didn't get to. It just didn't process it before it found the goal, so it just was left out, if you like. But 0 is very interesting because 0 doesn't have a parent. Now that's very important. That's what you want, because the one thing I didn't say in that earlier description of when you print the path back to the root and you have some kind of recursive thing going on to get back there, How do you know when you're at the root? You don't want to segfault and go off the end of the array in some way. How do you stop? Well, the one thing you know is you have visited and calculated the parent, or put the parent of every node in the parented array at every step. So when you go backwards, looking at the parents, they're all defined because they all had children and you put the parent in you. They would only be non-negative if you actually process them, so they're all there. Then none of them will be negative, except, of course, the original parent, the root, which is somebody who doesn't have a parent. So that stays -1. And that's the trigger to stop the recursion. So that has to be mentioned. So the array parent stores the parent of every visited node, except the start, which has no parent. Now, printing the path is not trivial. In line 61, we have the goal. Say that again, we have the goal. We want to print the path from the start to the goal. So we need to somehow go back up, but not to also forget that we're at the goal. We've got to do it and sort of remember where we've come from at every step. And we do that just by using a recursion. It's head recursion, and basically print path calls itself immediately. So print path calls print path, it's recursion, until it reaches a vertex which has a negative -1 as its parent. And that's the root. And if it gets that vertex, it can then immediately print the identity. So the first node it prints, when you do the recursive call print path, is the root of the graph. Because you're not allowed to print, you're calling yourself every time, print path, print path, print path, print path, print path, print path, all the way up the graph when you're all over there, and then you're over there, and you're trying to find the path back, and eventually you keep calling print path, and you're just getting bored and calling print path every time. When am I going to do something? I'll keep on stacking on the system stack all these calls, and eventually when I get to the top and I've got a -1 parent, I've hit the root, I stop, I now have my base case. I have the original node, the starting point. And then I can print that node, 0, presumably, and then I'm terminating each of the calls. Just naturally, they all fall through, and you print the node as they unravel in the reverse direction. So here it is. It looks simple, and you see in line 2, print path. In line 5, is calling print path. And print path has a vertex v as the last argument, and line 5, when it calls itself with the parent of v. That's classic head recursion. Calls itself really quickly every time. And it will continue to do so as long as the parent is unvisited. If the parent becomes, the parent unvisited is a terrible thing now, but I'm using the same -1. That's just -1. It's not equal to -1. So as long as you have a parent, you go back. But the moment it becomes visited, in other words, it's -1, unvisited, it becomes -1, you print that node, that vertex, and that will be 0. So then that last call, if you like, that's what I call it, the last call will print here first. It's the first thing that's done, and it's the last call. Now, every other one is stacked up on the system stack. And then comes through, okay, it's now printed, and that's come back to the previous call, and the previous call said, okay, I've done that, now I print the arrow, and then I print the node next level down. Then that call's finished, and then the previous print path terminates, it comes back and says, okay, I've got to print an arrow, and then node number, and print an arrow, print a node number. Every time you unravel the calls, you print the arrow and print the next level down. That's classic head recursion. Very nice little function. And the result is just that little thing there, 0, 5, 4. We're at 4, we called recursively, using head recursion, from 4, it went back up to the parent of 4 is 5, parent of 5 is 0. At 0, we have a parent of -1, stops the recursion, and prints the 0, and then prints the arrow and the identity of the child, and then another arrow and the identity of the goal, which is where we started from. Long explanation for a little bit of coding there, which has got nothing to do with depth first search. It's all about how you do recursion. Okay, that's the shortest path algorithm. That has told us in a graph, random graph, millions and millions of nodes, if you like, how you can find the shortest path between just node X and node Y. Any two nodes, anywhere in the graph. Okay, and well, even stronger than that, with any node, even if it's not in the graph. So it'll just say there's no path. And it's guaranteed to give you the shortest path. Okay, there'll be no shorter path than that. So there may be different paths which all equal that. So there may be many paths which will all be equally long. But there'll be nothing shorter just by being bad first. It is nothing more really than a slightly modified BFS quack. The modification again is in the cushioning and the popping is exactly the same as before. The modification is in finding the goal and recording the parent. See, those three lines there are really 51, 52, 53, 54. They make it shortest path. And of course, if you're going to have a parent, you've got to create it, and that's what you do in the function before. You've got to create it, or up the top of that function, function 4. So the parent is created up the top there, line 36. But that's just housekeeping. Okay, so those few lines there make it a shortest path algorithm. But in essence, it's just BFS quack. Now, that's the BFS application. BFS application. Cycle detection is where it gets more interesting. It's still pretty boring, and there are many better ways of doing BFS, shortest path, than BFS. I mean, it's still a brute force method that looks at all the children. Okay, it's still pretty brutal. No sophistication there at all. There are a lot of other algorithms which can do it better. Now we look at things like, if I've got this graph, is it possible the graph is a tree? And that can be really interesting. You want to know, is this graph got any cycles? If it's got no cycles, it's a tree. You think about it. If I take any two branches, if I never meet myself again, that means I run to a leaf. Well, that's what a tree is. I reach a dead end. So every branch is a dead end. And that's what a tree is. And at the moment I cross and hit myself somewhere, I'm no longer a tree. That's an extremely important problem, an extremely important property to know. When you have this very complex graph, which is just in massive numbers, God, is that a tree or a graph? How do I do that? How do I know? It's actually extremely simple. And this DFS, and BFS could do it too, but with BFS, you're going to do the whole lot. And if there are millions and millions of nodes, oh my goodness, that could be terrible. You know you're going to do the whole lot, possibly doing the whole lot, if the cycle is way deep, so before you actually get back right down the bottom. DFS is much faster because it goes deep looking. That's the whole story. So the recursive DFS algorithm, here it is again. I want you to have that imprinted in your brain. This DFS recursion, this is not the quack version, this is programming version, where we set up visited, we set up order, then we look for all the adjacencies of the children, and if there's a node, of course we're only interested in ones that are connected, so is connected, is it adjacent? If it's connected to the node that we're currently at, then we want to go down that path too and have a look what that path has got, and that's where we call DFSR again with the child W. So W is the child, and it's here, and W takes the place of, if you like, vertex V there. So vertex V is the original call, child is W, we explore W, and then one of W's first children, and then we keep exploring children until there are no more children, then we come up and explore another child, and we keep on exploring children until coming up the tree, okay, up the graph. We don't know if it's a graph or a tree. How can we use this to find cycles? Hang on, which version have I got here? This uses the graph ADT, but not the quack ADT. Okay, this is just the recursion, programming recursion. To search for a cycle, just like with the BFS shortest path, we just have to change the main program to, instead of call DFS R, or DFS recursion, we call has cycle. I forgot what I've called the thing. has cycle here. So we have a recursive routine which is very similar to DFS. So there was DFSR, here now is has cycle. Now has cycle is almost identical. It sets up, let's go through this slowly. Here's the main program, search for cycle. The search for cycle is visited. Bring back your thoughts now to DFSR. Visited, an order gets set, and then whether it does recursively, it calls has cycle. So this is a wrapper on a recursive routine to actually walk down or traverse the tree, or the graph. If has cycle comes back with found, if it's true, then it's found the cycle. If it never comes back with found, then there's no cycle. And here's has cycle. This is the, you can compare with DFSR. DFSR sets up visited, an order, and then does a look on the children. If there's an edge and it's unvisited, it does that edge and returns the value. The big change here, in a sense, is when you recurse and you call yourself every time, you're looking for something, you have to know when to stop. Well, you know when to stop when you find the goal. Now, the goal is something that's visited before. So if you see something that's visited already, hey, I've visited that node before, that's not allowed. I must have a cycle. Okay, so the goal is at finding a visited node. So you see in line 59, it's, if you have an edge and it's unvisited, you call DFSR, which is has cycle, and you return the value. If it's not unvisited, then you've actually found the edge. We have revisited a node, hence we've got a cycle. So line 60, which is a comment, says at that point, and that's a detail, we don't want to actually include the fact that we've just come from the node. So we've come from a parent. We've already just visited the parent, of course. So when we look at the adjacencies, when you look at the adjacencies of a node, you want to exclude the fact that you've just come from a node. Of course, the parent is an adjacency of every child. And you can't, so you don't want to take that into account. So you have to ignore where you've just come from. So that from V there in line 59 is excluding the parent. So all of the other children, if any of the other children of your dad has been visited before, you've got a problem. There's somehow, some other path has got there, so they've been affected. They've been visited before, so you know you've got a cycle. So every child you see in your DFS path, or depth first path, must come, or must meet, or must see unvisited children. Okay, the moment you visit a child again, you see somebody's been visited, you know that you've got your cycle. And that's what that little else does here. So you keep going deeper and deeper, and of course when you do that, when you do know, oh, is it visited, that's the else, oh, I found a cycle, I must have gotten here earlier, I've been here before, in some other depth first search, on some other branch. What I need to do now is stop. And to stop recursion with information that you want to change way back up the top to tell the thing that was calling you way back up the top potentially, you must pass back information. And in this case, what you pass back is the fact that you found it. So return value is 1. So the return value being 1 is a condition on the loop 52, the iteration. You stop that, you don't look at any more children because you found the cycle. There's no point going on any further. Whether you've done 1/10 of the graph, 1/100th of the graph, or all the graph, it doesn't matter. You stop the whole thing. Stop processing children. Return value is 1. You stop the loop and you return that to the previous call. And the previous call goes back, and the return value gets passed back up the recursion, right up to the top. If it never does this else, return value stays 0. So every has cycle comes back with a return value 0. So just one else, one vertex that you visited before is enough to set found to 1, and that particular, and when you come out of the recursion, it just unnaturally unfolds. All the values get passed up the tree, and if just one found is true, then the whole thing will be true. You found your recursion, so you can report that. What differences are there in hash cycle compared to that? Really, hash cycle and DFS are very, very similar. Using a variable find or found to end the search, we needed to do that to terminate, so that ret value here is set true by that value there, and that terminates that loop. We don't go through that loop anymore, that for loop, it finishes. We separate two conditions in the for loop. If VW is an edge, then if W is unvisited, then we recurse, in other words, to keep searching. Else, and that's the big else here, else we've seen it before, it must be visited, and we have found our cycle. That's the line 59. And we just want to avoid going backwards along exactly the path we've come from. Your parent is excluded from the visited. Compile it, hash cycle with the helper and the graph, and when you run it, I call this little program here, little data file example dead. It's dead ends, and this one's example something else. What do I call that one? Example cycle. 1, 2, 3, 0, 0, 1, 2, 3, 4. So they're almost identical except for one extra edge. You see the extra edge is in there, 2, 0, 3, 1, 3, 4. Here you see is the 2, 1 in there, 1, 2, 2, 1. And that's that edge there, 1, 2. So that second graph here has this extra edge. It finds the cycle, and here there's no cycle found. Found is always 0. Ret value is always 0. Now, this is lots of applications. It gets pretty hefty, and there's a lot of programming. You can sort of see, in a sense, why all of this work on linked lists and quacks and programming that we've gone through in this course, this heavy programming, this is all what it's preparing you for. This stuff here. This is detailed, it's complicated in a sense. It's oh so simple when you see it a dozen times, and when you do the shortest path, you do the BFS, you do the recursion, you do the quack, and then your shortest path, or you do the hazard of cycle. They're all just flavours. It's like having ice cream with different colours, and they're all ice cream. I mean, there's no chicken kebab here or something else. It's all ice cream. It's all the same thing, but they have different flavours, and you sort of see the pattern, the similarities in them all, and you can get your head around them really quickly just by looking for a few crucial things. The most crucial, I think, is that the thing that actually should be the thing that you want to have in your head is the thing right at the, I shouldn't have done that, should I? Is the DFS. There's print path, that was just an abstraction. I thought I had it up the top there. The original DFS, doesn't matter. Oh, where am I? Oh, yes. The original DFS was actually extremely important, and that's the sort of the benchmark. Everything goes against that. The BFS is not that popular, not that often used. It's an application. DFS is used a lot, and you can do a lot of things with DFS. Okay, what we're going to do now is Eulerian cycles, and there will be a great question in the exercises on Eulerian cycles. I like Eulerian cycles. There's something really nice about them. There's symmetry, cleanness. An Eulerian path is a path that includes every edge exactly once. Now, how can you remember that? Eulerian is E, edge is E, E, E. Eulerian edges. So the idea is you want to, in a cycle, you have to start and end in the same point, and you want to go through every single edge in the graph, and you don't care how many times you visit the node. So if you have one star node in the center, you can go out there, boom, 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 and boom. Boom, 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 and boom, 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 boom. And you keep on going in all of the ways out, like the star pattern, and eventually you've done all of the vertices, and if that's where you start, that's fine. If you came from somewhere else, you go back to where you come from, and that's it. Now, if every vertex has even degree, then you can always draw an Eulerian cycle. every edge will be hit. So if you have vertex of degree 2, well, a big polygon, a square, a rectangle, a triangle, a pentagon, hexagon. Start it, boom, 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 boom. That's not hard. Square, boom, 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 triangle, boom, boom, boom. Big deal. Okay, now let's put a cross in there, a node, and then we say that's got 4, obviously, that's fine. And we've got a node up there, node up there, node up there, node up there. They're all 2, so we can go boom, 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 boom. Don't think I did that very well. But you get the idea. So I've got 4 there, all the others are 2, so I'd be able to go around and do all the edges. Yeah. An Eulerian cycle is an Eulerian path that ends and starts at the same spot. So an Eulerian path is something that isn't all even. It's all even except for 2 nodes that are odd. And those 2 nodes that are odd are start and end points. That's an Eulerian path. So if you've got them all even, Eulerian cycle. If there are 2 odd nodes, Eulerian path. If there's 1 odd or 3 odd, you've got nothing. Empty-handed. So a graph has an Eulerian path if all its vertices have even degree, except 2 that have odd degree, and has no Eulerian path if there are more than 2 vertices of odd degree. If there are more than 2, has neither Eulerian nor cycle if there are 2 with odd degree, more than 2, cannot be both. You think about an Eulerian path and Eulerian cycle, they include each other. Because if you've got it all even, well, you're not going to have a start and an end point. It's the same place, but it's not allowed to be the same place. The path is not the same place. So it's not a special case. So it makes Eulerians a bit strange. But they are what they are. So here are examples of Eulerian paths, and they have names, quite common names. Box, bow tie, prop bow, it's an interesting one, propeller of bows, like an aircraft propeller, and concurrent or something, I forgot what the conc's for, concatenated squares, squares, forgotten. Anybody know? Top of the head? Concurrent? Don't think so. I can't see that. Is it maybe a concentric. I did know once, but it's been too long ago since I actually thought where con comes from. But I suppose you'd have to know prop doesn't mean property, it means propeller. And I'm pretty sure that was propeller. I thought that was very interesting, propeller. So they're all very simple to actually work a route. You start there and you go up there, 7, 0, 7, 8, 9, 5, 6, 10, 3, 4, back to 10, down to 11, 2. You can sort of see really easy to do. And there you can also do quite easy a route that starts and finishes at the same point. Now, what's the algorithm for this? To find an Eulerian path. An interesting problem in logistics. Can you cover every edge once and you don't care how many times you visit cities? As long as you do every road once. Every road means maybe road maintenance, maybe something to do with GPS. You want to know that you've covered all the ground. Coming back to some central point to get you stock or whatever. So this is a really interesting real-time problem. So you read the Eulerian graph, read the graph, it's got to be an Eulerian graph, it's got to have all the vertices of even degree. And you initialize a stack. And you pick any position, any node you like in the graph, usually 0, but there's usually a 0 there. Certainly in our notation and with our graph reading, there must be a 0. So while the stack is, we choose any vertex and we push that, just like DFS, just like BFS. While the stack is not empty, if the top of stack has 1 or more adjacent vertices, so if there's an element on the top of stack that has no children, we just pop him off. So what we're looking for here are childless elements on top of the stack. If they have children, we put them, hang on, we've got to get this right, else pop the top and print it. If the top of stack has 1 or more adjacent, I did it the opposite way around. I always find it interesting. When you've got the isolated, and that's the thing we're looking for, a vertex with no children, we pop him and print him. We've got him. That's the one we want to print. When they've got children, we've got to keep on going and process it. So we're looking at going through, it's a bit like depth first. We're trying, and this is a depth first application, we keep looking for more children, children. You keep on going, looking for children, until you get something which is childless. And that thing, when you put it on the stack, if it's childless, then you know you've got to start doing something. Until then, it's just pushing onto the stack. So we select, in this case, arbitrarily the largest W. If you've got a bunch of children for a node, you push it onto the W. And what's really interesting, and you think, oh my goodness, I didn't expect this, you remove the edge. And we haven't done that before. And that's sort of the way of thinking about this. And it makes it really interesting. In some sense, you destroy the data structure, and by destroying it, you actually find out something, if you like. But it's actually the algorithm. It's the construction algorithm is to destroy it. So it's depth first with destruction, gives you Eulerian, if that's the way you can remember it. So we remove the edge to the child, and then the child's child. We push, remove the edge, push, remove the edge, push, remove the edge, push, remove the edge, till we get to a child on the stack that's got no more children left because all the edges have been removed to it. It's been isolated, orphaned if you like, and that is one that can be taken out. So you pop them. Okay, and then you go to the next one on. You keep popping as long as you've got childless nodes. Eventually you'll get to a node on the stack that's still got children. And then you start processing them and you put them back on. So as long as they've got children, you keep on pushing. When you pop, you pop when the children have become orphaned. Why select the largest vertex here? Well, there's no actual reason for it, because if you think about it, in any of these things, you stop it. For example, this one here, 0, 1, the bow. 0, 1, 2, 3, 4, 5, 6. What a weird way of labelling it. You'd not normally label the graph that way because it's all over the place. But it's been labelled in a way so that when you use the largest child goes on to is the one that's processed first every time, then you get a particular route through the graph. If you think about it, if you start at 0, how many different ways could we actually, how many Eulerian paths are there? You can go from 0, 1, 6, 9, 6, 2, 9, 5, go away, 4, 3, 2, 0. So we treat it as a big bow tie, and then we've got one Eulerian path. We could have gone 0, 1, 6, 2, and then 3, 4, 5, so upside down bow in a sense. And we would have gotten back here and had an Eulerian path. Or you could have done 0, 2, 5, 4, 3, both of them upside down, 0, 2, 5, 4, 3, 2, 0, 1, 6. So you've got up and down, if you like, for both sides, so there'll be 4 different Eulerian paths. That's pretty right. So which one do you take? Well, it depends how you label them, and it depends on the strategy. If you take the strategy of the largest, and that's the strategy that they say here. This is the strategy I say here. You take the largest. Select arbitrarily the largest vertex in that first black bullet point, arbitrarily largest vertex. So here it is. While it's not empty, we pop the top element of the stack, which was originally the starting element, so we did a push, 0. We pop 0, we push the 0 back on, and then we look at the children. We need to put it back on again. We have the identity of the V. So we pop him and push him, and this is really a bit tricky. I looked at that this morning. I thought, oh, what was going on there? Why are we popping and pushing? What's the point of that? Well, we need to see who's on there. This is a repeated thing. So who's on the top? We pop him. Oh, that's who it is. Push him back on again, because in the loop, in the if statement there, if there's an edge to a vertex W, then we want to push that W, push the child on, and then we do the removal. Oh, I've got the old version of remove there. Ah, goodness gracious, there's another version. That's remove edge. That's right, isn't it? Remove edge. Is that right? Yeah, that should be remove edge. Yes. She was helping me this afternoon. I had to change all my e's to edges. So that's remove edge. It doesn't matter. I'll have to change that later. So we do a remove edge, and we continue else if we have a child that doesn't have anything adjacent. So if W, which is the child, is greater than or equal to 0, we do a push and we move, else we do a pop. And the question is, what is an adjacency here? The adjacency is just get the new edge. Do a new edge. If that edge is there, I've changed all these, fortunately. New edge is edge. Return the value of that vertex. So we're looking for the biggest child there. Vertex W is num v minus 1. Start from the right on the biggest number, and we go back down, all the vertices looking for the biggest vertex, which is adjacent to this node. And if it's adjacent to this node, we return it. And then it goes into that line 10 there. So that is now Eulerian. Come on, talk to me. Oh, now you're going to do that to me again. It actually, when you look at a simple little example here, which is, this is the box. This is now for the box graph above. We push 0, push 3, and remove 0, 3. So we start with 0. The biggest vertex adjacent to 0 is 3. We push 3, and we break the contact, the connection, the link, remove the edge 0, 3. We then push 2, because 2 is the biggest neighbour, the only neighbour, adjacency of 3, and then we break 3, 2. Then we push 1 as the only neighbour of 2, and we break 2, 1. And then we push 1, did I just say that? And then we break 0 to 1, and we've got 0 left. So 0 is on the stack again for the second time. But 0's got no children now. It's the first time we've got no children at all. So we pop 0, and we're finished, and then we check the stack again. It's still not empty. We pop 3, then we pop 2, and then we pop 1, if I got that in the right order. Maybe it was pop 1, 2, then 3. I've forgotten which order already. So we pop the other way around. I thought as much. Pop 1, 2, 3. So we push, remove, push, remove, push, remove, push, remove. 0 is now disconnected on the stack. So when it's disconnected, we print it, we pop it and print it, and we look at the stack again. We see that 1's disconnected, we pop and print, 2's disconnected, 3's disconnected. We've disconnected them ourselves, and that's the whole idea. Okay, when you break the contacts, break the edges, break the links, then you can actually see what's left. And when they become completely orphaned, that's the position, or that's the one you print out, for each one as they become orphaned. So slightly more complex cases. There was no backtracking here. It was a really simple case. Here's another case where you have 0, 1, 2, 3. That was that one. So we go to the bow when, depending on the way you go, you don't have to. You can actually not require backtracking if you take the outside route. 0, 1, 2, 0, 1, 6, 2, 5. If you took that route, there'd be no backtracking. But if you take the route 0, 2, 6, 1, 0. Now, I'm not sure who's with me here. Might be too many, I suspect. If you start at 0, the children of 0 are 2 and 1. Put them on the stack, 1 and 2. You go to 2. Then it has children 3, 5, 6, and 0. You go to the biggest, which is 6. Didn't want to go that way necessarily, but okay, I'm up to 6 now. Then you put its children on, which is 1, and you break the link. So we've broken 0, 2, 2, 6, and 1, 6, 1, and then we come back to 0 again. So 0 is now completely isolated. We've broken all those 4 links on the left-hand side. So that means we print 0, and we print 0. We've still got 1 on the stack. That's isolated now. So we print 1. Then we go to 6, we print 6, and we go to 2, but 2's not isolated. 2's still got 2 children, 3 and 5. So we have to put 3 and 5 on the stack, and we take the biggest of the 2, which is 5. So we go to 5 now. 5's got 4 as a child, so we go to 4. 4 goes to 3. We break the links every time. 3, we go to 2. And now 2's isolated because we've broken all the links. 0, 2, 2, 6, 2, 5, and 3, 2. So 2's isolated, so we print 2. So actually what we've printed is so far 0, 0, 1, 6, 2, and then we find now that I think 3 has been isolated, then we print 3, then 4 has been isolated, and 5 has been isolated. So the route is a bit of a strange route, but if you do it the wrong way, if you like, you need backtracking once. You get back to a point where a node's still got children, and you've got to increase the size of the stack again. And if you do it another route, then that doesn't happen. You just keep it adding, just as if it was a square. Keep on adding, and you eventually have to unravel the whole lot. And here, you do backtracking, I think, 4 times, or 3 extra times. Start there 4 times. Every time you finish a little loop, then you have to backtrack to get up here again. And when you finish that little loop, you backtrack. In other words, you've got to find a previous child, an element on the stack, which has got more children. So that's the bow, or the box. No, that's the box, that's the bow here. And the prop bows, the big one, you see that it's push, 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 pop, 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 and remove, here are the things on the right here. Removing, 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 printing, 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 removing more, so there's a backtrack happening there, there's a backtrack happening there. And that's the Eulerian cycle for you. I couldn't, so you think, okay, what's it, okay, what are we achieving here? Well, this is what we're achieving. This is just a GIF, a moving GIF. But there's a complex graph there. That complex graph, they're all even vertices. And there's that algorithm applied to that. They've got to be numbered in a certain way. And you could have thought, when you looked at that first, you think, how does it know where to go? What's it doing? Where's it going? All over? It looks like it's a human or it's thinking, or what the hell is it doing? Is it random? And what is it doing? Well, it's just stacking. It's just got a DFS with a stack, removing edges, figuratively speaking, and as it removes edges, it's seeing which children are orphaned. So when you see that now, when you see a path through a complex graph, which looks like it's got its own mind, its own intelligence, it's just a simple application of DFS search where edges are being removed. In this particular case with Eulerian cycles, edges are just being removed, isolating vertices, and when they're completely isolated, it prints them. And that's what the basis of that Eulerian algorithm is. It would be interesting to reverse engineer now what the labelling is. That's really a cruel problem. Because if you think about how many vertices are there, well, there's quite a few, say there's 40. And how many possible labellings are there? Billions. So you've now got to work out which of these, so you know where the starting point is. I suppose you call that 0. And then you've got to work out, okay, it's done that route there, therefore 1 and 2, and you've got to work out what's going on the stack at what point and why it's chosen this one, so you know what the neighbours have got to be labelled as. And I suppose you could work out then, maybe it would take you a couple of hours, what the labelling must have been for that particular algorithm to work. It's sort of nice. It's nice when you understand that something isn't mysterious anymore. It's actually very simple. It's only, 50 lines of code, and you've got it. And it's, in fact, quite dumb. Ooh, I don't know. That was an Eulerian cycle. Oh, we've got a bit of time, that's good. And that's actually, in some senses, complicated, as complicated as it gets. Because after that, it becomes a little bit crueler, in a way. I then go back from the harder to something which is just make sure I'm in the right spot. Depth first, we've got another application. Hang on, we just did a cycle detection, trees. That's what we just did. And then we did Eulerians. And now we've got to the next application, which is finding a path. Just find a path between two vertices, a goal, and a start. Start and then a goal. It's a bit like breadth first, but it's now using depth first to find a path. Is there a path between two vertices? Anywhere, any length, just can they one be reached by the other? Interesting problem. This one, I could have had this one earlier, but I haven't because I don't want to give you all the code here. And the next problem again is even in some sense worse. They're simpler, so the rest is actually not going to take me long now. You've seen in some sense enough from these BFS quack and DFS quack and DFS recursion. They're the three basic algorithms. The two quack for the BFS and the DFS, and the non-quack, which is recursive DFS. And all these algorithms that you show with shortest path and Eulerian, these are all variations of those themes. They're all just changing code, changing name, adding a search, adding a goal, I found it, getting out, that kind of programming stuff. It really is not interesting from an algorithmic point of view. They're just the same algorithm with different flavours. This one is no different, and in fact it's actually quite a bit simpler, so you might breathe a sigh of relief. So, okay, these one I can understand even more, because Eulerian was it's a bit funny, it's a bit different in the sense that you're removing edges. Here we've got the DFS algorithm again. I wanted to show it to you again. Remember what the DFS was? You set up in the first line here, this is the recursive call, this is not quacky, this is all pure recursion. We do the visit, we do the order, we look at all the children. If there's an attached child, well, the children are the attached nodes, you call yourself, and that builds up the stack, does all the children, looking for something. This is the basic building block of DFS search, and all of these applications are variations on this really, unless they're using quacks, but there's still a variation on it. What we want to do is find a path between two nodes. So we have a starting point and we have an end point, a lot like BFS, starting point and an end point. We pass the goal vertex to the recursive function. We test if the current vertex is the goal. So when we pass it, we traverse the DFS, the graph. We look for the goal. We return success if that current node is the goal, and we do that by passing it up the value, up the tree of recursive calls, which is retval. And the only other thing we need to do is change the name. It's a very simple adaptation. So that DFSR here, stock standard DFS we saw in the previous lecture, has now become isPath, where isPath now has an extra parameter. This is not BFS, shortest path. This is DFS, is there a path? Okay, it's different. And BFS, shortest path, use the quack. And this is DFS, is there a path? Recursion. They're different. My goodness, they're very similar. So they're both ice cream, just different flavours. So here we have a vertex v and the goal that we're going to. The goal doesn't change, but the vertex v will change when we call isPath. isPath called here in line 12. So we see in line 12 straight away W here instead of V. So V goes to W, and W is, of course, just simply a child. Now, is that child reported true? Then we pass that back. So here we're reporting that we've got child as W, and we return found. So the found equals isPath, return found. Found is set to 1 in the isPath that finds that V is the goal. So we keep on going down the recursion, up the recursion I suppose you could say too. Keep on following the recursion. Every time you get to a new vertex, we check whether it's the goal. Look at the children, a child, take the child, is it the goal? Look at the other children, still no goal. Take the children's children, look for a goal. And eventually, if you do find the child, which is the goal, then you say, I found it. So that found equals 1, and the return found passes it all the way up again, because every return from DFS will pass that found. If isPath returns true, or found equals 1, then this found will be 1. So it passes the information back up, and that found goes up to the next isPath. So it gets passed right up to the top. So there's isPath. I don't show you the main program here. It's trivial. It just when you call DFS from the wrapper, remember there was a wrapper there which set up visited and order and calls DFS, it now returns a value, found, and if it's found, and you say, I found it, or it's not found, and it says I'm not found. If it's found is 0, then it's not been found. The function does a DFS traversal, exactly like DFSR, but at the same time it searches for a node, so it's quite simple. It's actually one of the simplest applications here. Just as BFS shortest path from earlier, visited may be incomplete. It comes out here, bombs out here, is path, says, okay, I'm found, sorry, what am I saying here? Here, when it finds it, returns 1 and doesn't do any more searching. So all of the recursions, they have to just terminate, basically. So everything just comes back immediately from where it was. It doesn't do any more children at any level. So visited will probably be incomplete. There's a wrapper function, which we had before, with just DFSR, the vertex, size of the graph, and order and visited. Of course, that's our wrapper, called the recursion. That's what the wrapper does. It calls the recursion and lets the recursion do its thing. And then it gets the result and then passes it back to the main program. It's sort of the intermediary, the organizer. And isPath here is the call that comes in the wrapper. isPath with the goal and that current vertex, whatever that may be, we're starting off with found or not found. So here it shows that same graph I've used many times, path 3, 4, 3, 4, 2, 0. Oh, I've forgotten how this 2, 4. So 0, 3, 4. I don't even know what I'm looking for. Oh, start at 0 and goal is 3. Well, we won't go through that now. Finally, reachability. This is probably the most serious problem in research. You'll find that immensely often in various AI problems, in theoretical problems, model checking, all sorts of situations where you have huge amount of data that's got to be processed and you're looking for some property. You want to know, is something with a particular property, does it exist anywhere? Is some state of the system reachable where this is true, this characteristic, this property is true? It's immensely important. You want to know, in all of the things that can happen in a particular process, whether you can ever get to a state where, for example, the hardware locks. And you can describe locking hardware in a certain way. So you can describe all of the behaviours of the system, and you want to know if all of these behaviours together can give rise to a node in a graph which has a certain set of properties, which is an undesirable situation that you don't want to see. So if you can get there, you've got a problem. It means it is feasible, theoretically feasible, to get to a bad state. So you'd have to change a design to make sure you can't get to that state, and then you do a re-evaluation, find out if a bad state is reachable in another system by modifying the system. So reachability is immensely important. So in many problems we are interested in knowing whether vertices are reachable from the start state. And here we have two examples of quite a complex tree, but you can see 17, 18, 19 and 8 are isolated. You can't reach them. Now, if they were bad states, that would be good, because you don't want to be able to reach them. If they're all situations where the system locks up, or it crashes, or it overheats, or something happens, then that's what you'd want. Now, the question is whether those states are reachable or not, because you don't know whether they're reachable necessarily. All you know is that those states are possible, but are they really reachable, or are they isolated? And here's another one here where you have two graphs, a very simple square line, a square and a line. The names are quite interesting. So some of the vertices are unreachable from the start state 0, and others are not. If the graph is undirected, it is obviously disconnected. In other words, what you're looking for here, is it a disconnected graph or not? If the graph is directed, then it may not be disconnected, of course. It just may not be able to get to it by following the directions of the arrows, but that's another lecture, directed graphs. A DFS algorithm can be used to find all the reachable states. Simply run the algorithm from the start state. On conclusion, check that the visited array, any vertex that is unvisited, is unreachable. So when you've done a full DFS search, you just check the visited array, and you'll see whether any state has not been visited in this connected graph, if there's anything left. An alternative method, and that's what I want to push now. We've seen that. We haven't used that as such to achieve anything. We just say, well, okay, if there are vertices we haven't seen or we haven't visited, it's got to be disconnected. We'll have to restart it. That's where I started this lecture. We restart the whole search on the other components. So, in a sense, what we're trying to do is traverse everything. Now, the issue of disconnectedness becomes important. We want to know whether there are unreachable states. So we're not going to use DFS. We're actually going to use what's called the fixed point algorithm. And this is what I want you to implement in your exercises. Fixed point is very simple. It sort of sounds a bit strange, but it's a very simple concept. Is when you have data, you change data by adding to it as much as you possibly can. And you keep adding to the data as much as you can. When you find you can't add any more, then you've reached what's called a fixed point state. It's a state of the system where it's not going to change anymore. It's the fixed point. It's the end point, if you like. And any more data that comes in, you know it's not going to affect it anymore because it's reached its fixed point. So we initialize a reachable set comprising just the start vertex. So you start with 0, presumably, and every other vertex is considered unreachable. Check every unreachable